Okay, this is GCSE Maths, and we're looking at circle theorems. You should be able to understand circle theorems. We're going to go through the proofs of some of these as well. So our theorem 1 is that the angle at the centre of a circle here is twice the angle at the circumference when they're both subtended by the same 2 points, i.e. AOB equals 2 times ACB, and they need to come then from the same 2 points. In terms of a proof, it would need new diagrams. You can see I've drawn out pretty much the same thing here. And we need to do a wee line going through the centre here to see if we can suss out what's going on. So you see we've made 2 triangles here. I'm going to call this wee bit here X, this wee angle in here, and this wee angle in here Y. Alright, so that's us then to start with. As you can see, then we call this out as well, obviously. So CAO has to equal X. So why is that? That's a radius, that's a radius. So what we have here is actually an isosceles triangle, so this has to be an X here. And for the same reason, CBO equals Y. So we have that. This angle here, AOC, therefore AOC must equal 180, take away these 2 angles, so it's 180, take away 2x, because angles in a triangle equal 180. And similarly then, BOC is 180 take away 2x. Sorry, 180 take away 2y then. That's going to be, so that's going to be 180 take away 2y. That's going to be 180 take away 2x. I hope you're still with me here. That means this angle here, which is the angle AOB, is then going to be 360 take away 180 take away 2y plus 180 take away 2x. If you tidy all this up, you of course then get AOB equals 2x plus 2y, which equals 2 upon x plus y. We've just about fitted in there, was because I had to draw this other one in here. But that's our proof, because that is twice now your angle here, which is x plus y. Under our second theorem then, angles on the circumference in the same segment subtended by the same 2 points are equal. So because these two are subtended by the same 2 points A and B, then these 2 angles here must be equal. And it doesn't matter where you put your C and your D, we can kind of go over here or over here. Those 2 angles then must be the same as each other. I've added in a wee O here and put in then a 2x, and hopefully then we can get some sort of proof from there. Not really too much to this proof really, but we're going to let AOB equal 2x. Therefore, ACB must equal x, because of theorem 1, which is above, and that's that the angle at the centre is twice the angle thing. And ADB must equal x, because of theorem 1 above. Therefore, ACB equals AOB. Just another quick point about that, if you can try and not see this wee bit, but it actually means that this angle here is going to now be the same as this angle here, because it's the same rule. If you don't take the 2 points A and B, you go from there to there. Instead, if you go from here, then those 2 angles are going to be the same as well. Theorem 3, every angle on the circumference of a semicircle is 90 degrees, and it's effectively just the same thing again. There's our O. So angle AOB is 180 degrees. Therefore, angle ACB is equal to a half of 180, which equals 90. And that's because the angle at the center is twice the angle at the circumference. And again, it's just me writing out theorem 1 effectively above. Just a couple of examples then. So we know this one here is 25. That means the angle at the center is going to be twice 25. So y equals 2 times 25, and that equals 50. And angle x, these are both taken from the same 2 points. This goes to this end, this goes to this end. Therefore x must be 25 degrees as well. On to example B, we have 5x and x. Note this is like our third theorem. That's a diameter, so that means that must be 90 degrees. That means that these two must add up then to give 90, because 90 plus this gives us 180. So 5x plus x must equal 90. 6x gives me 90, and x then must be 15 degrees. Example C, again reasonably similar. It just looks a bit funny here because these points have kind of been brought all the way around, but it's the same rule that this angle here is going to be twice this angle here. So y is going to be half of 240. So y then is going to be 120. So cyclic quadrilateral is in. This is going to be theorem 4. A cyclic quadrilateral is a quadrilateral whose vertices all lie on the circumference of a circle. So here be one here, 1, 2, 3, 4. And what we're saying that opposite angles of a cyclic quadrilateral always add up to 180. So this one and this one add up to 180. And this one add up to 180. So here be the proof for this. But let this be O. And I label this in A, B, C, D. We're going to let A, B, C equal x. Then A, O, C, and that's the outside one, must equal 2x, because angle takes a long time to write this. Angle at center equals 2 times angle on circumference. So that angle there must be twice that. And we've already worked out that. That means then the other AOC must be 360 take away 2x. So that would be the obtuse one. So let's go for a reflex here just to explain. So the reflex angle is at 2x. Then so the obtuse AOC is 360 take away 2x. And then therefore AD, that's me doing a very bad D, must equal half of 360 take away 2x, which is 180 take away x. Again for the same rule. Because the angle here must be twice this angle here, and so if you start off with an x here, you always end up here with 180 minus x. So say for example then that this was 60 degrees, this would be 180 take away 60 and would give us 120. Example 2, find x and y. So again, here's our cyclic quadrilateral. All 4 corners are tercing the circumference. That must mean that x is 180 take away 72, which is going to be 108. Angle y we need to be a wee bit careful with here. This is 125. Of course, this isn't y. This is the one we're looking for. Let's call this P, just at random. P is going to be 180. Take away 125, which is 55, and therefore y is 180 take away p, which is 180 take away 55, which is 125. Maybe that's very obvious to people, but just be careful you don't write 55 for that, because it's not the angle actually inside the quadrilateral. This angle here is always going to end up equal to this one here. Two quick theorems then to do with tangents. The angle between a tangent and the radius at the point of contact is 90 degrees. Tangent here, that's a bit just touching the circle, and a radius drawn on from there, that's always 90 degrees. The other theorem about tangents is that two tangents drawn from the same point to a circle are equal in length. So the distance, if you pick a random point outside the circle, for example here, then the distance from here to here is always going to be the distance from here to here. If you join them to the centre with a couple of radii, you occasionally get what's called then the tangent kite, and hopefully you can see then that must be a kite, because those two sides are the same length and those two sides are the same length, so that then would be your tangent kite, which is handy then to work out some other bits and pieces. Remember as well from a minute ago where we know then that that's a right angle and that's a right angle. Example 1, CD is the tangent, so there's our CD down there, and angle BCD is 35 degrees. Find OCB, so OCB, we can see there's our radius, there's our tangent, so it must be 90 take away 35. That's going to be 90 take away 35, which is going to be 55. And then COB, so I hope we can see as well. So how are we going to work this out? That's 55. That has to be 55 as well. Why is that? Because that's a radius and that's a radius. Those two add together to give 110. So COB is going to be 180 take away 2 times the 55. So we have our triangle there, so 110, so it's going to be 70. And then I assume we want CAB here. So CAB is going to be 70 divided by 2, because remember at the circumference is always half of what's at the centre. So that then would be 35 degrees. Example 2 then, PT. That's supposed to be a T there, it's very hard to see. PT and QT are tangents to the circle. The angle PRQ is 28 degrees. So PRQ is 28 degrees. Find angle PTQ. Right, so we know that POQ, what have I done? POQ is equal to 28 times 2, so we know then that's going to be 56. We also know that this is a right angle and this is a right angle, so it means then that PTQ is going to equal 180 take away 56, and that gives me then 124 degrees. Finally then there's our alternate segment theorem. So the angle between a tangent and a chord, tangent chord, equals the angle on the circumference in the exact opposite segment. So it always says that this angle here is equal to this angle here. This is very hard to see. I'm going to draw a couple of wee random ones out so you can work out what's going on. It's effectively with a tangent and a triangle then in the circle. And I can tell you my wee silly way of remembering it. So it's saying that this angle here is the same as one of the angles in the triangle. The way I remember it's a bit silly, but I remember that this angle here is the same as one of these angles. It's not going to be that one because it's right beside it. It's not that one because they're on the same line, the same edge of the triangle. So it must be this one here. Let's show it again in another example. There's our badly drawn tangent. And this angle here isn't the same as this one. Isn't the same as this one because it's on the same line, but must be the same as this one. So here's the proof. We have let TCB equal x, then BCO must equal 90 minus x. So why is that? Because tangent and radius are at 90 degrees. There's my tangent, there's my radius. So that means that needs to be then 90 minus x. Then CBO is equal to 90 minus x as well. Why is that? That's because it's an isosceles triangle. That's a radius, that's a radius. So that's 90 minus x. That means that BOC must equal 180, take away 90 minus x plus 90 minus x. Because how do you get this angle here? You get 180 and take away these two angles here, so it must be that. If you tidy that up, 180 take away 90, take away the 90, that just gives you a 0, and then minus minus x, so you just actually end up then with a 2x. The reason for that is angles in triangle add to 180 degrees, and that means then that BAC is equal to x, and the reason for that, angle on circumference equals half angle at center. And that's the proof of it there, effectively showing that that is x, so that must be x then as well.